Hello, this is part 2 of lecture 8, optimal detection of digital modulation with memory. Continuing off where we left off on Viterbi algorithm. So just to summarize what we talked about, well, basically the Viterbi algorithm is the optimal algorithm for in terms of computational complexity that implements the maximum likelihood sequence detector. And this slide is a summary of the Viterbi algorithm. So from the initial state at t is equal to 0, you advance the trellis until it reaches what we call the steady state pattern. So basically, that's when your trellis converges onto a certain state. Okay? If that's from your, if that is not clear, then you should look at the previous lecture. At each state, you compare the distances at the current time, or what we call the cost function of the paths going into that state. You choose this path that maximizes the cost function. Or when we say maximize or optimizes rather the cost function. When we say optimize, it depends on your definition of the cost function. If it's distance, you have to minimize the distance. Okay. And the remaining path is what we call the survivor path. At the end of the modulation, you choose the path with the least cost function and determine your transmitted sequence. We've applied this to flip-flops. And these flip-flops actually are basically just ones and zeros. Now, the interesting thing is, how do we apply it to continuous phase modulation? So recall that your CPM has a function, can be represented rather by a function v of t. This is the complex baseband representation of CPM. At a time t is equal to nt, the phase state, or rather the phase of your CPM signal is equal to this, which is an integral of your pulse that has a length L. So L denotes the memory that is present in your CPM signal. And basically that is just equal to some theta n plus theta of t. This theta n is the accumulation of all the previous symbols. Okay? If the memory is L, it's the previous symbols that has already finished the ramping up or the integration of their pulses. Okay? That's why the maximum value of the summation here is n minus L. We call this the phase state. Theta of t represents all the previous L bits, or symbols rather, all the previous L symbols that are still ramping up in their integral with their pulses, corresponding pulses. And we call this the correlative state. The state vector is now defined by the phase state and all the different uh, inputs. Okay, so that's in minus 1 up to in minus L plus 1. So this is, or these are L symbols. Okay, the next state is you just advance this, you just add 1 to all the indices. So the question now is, how do we define the path distance for continuous phase modulation? So the previous one is actually straightforward. In the previous lecture, the definition of distance is actually very straightforward. But in this case, for the continuous phase modulation, we're tracking the phase. How do we define the distance if the state vector actually has different, they have very different quantities? Okay, so this theta n is a phase, this I sub n minus 1 to I sub n minus L plus 1 are all symbols. How do we define the distance? Okay, consider then your passband CPM signal corrupted by some noise. The distance between R of t and S of t, so we're considering here time domain signals at a time t is equal to nt, can be defined by your signal space distance. Okay? So we won't be talking about breaking this into vectors. let's just take them as raw signals and then take the distance defined in terms of integrals. So you have this expression right here. If you expand that, you have this total distance for your CPM signal. Okay? So examining these three components, you have this is the energy of your received signal, this is the energy of your transmit signal, and this is the cross correlation of R of t and S of t. So basically the distance is a function of the energies of your received and transmitted signals and some cost function m sub n of I, which is the cross correlation of R of t and S of t. If R of t is exactly equal to S of t, that means your energy ER is equal to ES. And this cost function right here will just be equal to that energy. So energy plus energy minus 2 times the same energy is equal to 0. And that is the minimum distance. And this minimum distance occurs when we maximize this cost function between the two signals. So basically, we will only consider Mn of I since ER and ES are both constant. Okay? So we're basically cross-correlating R of t and S of t. This is the function that we'll use or that we'll maximize in terms of our Viterbi algorithm. When we'll use the Viterbi algorithm to decode a CPM signal, then we'll use the cross-correlation between the received signal and the transmitted signal. So with that, we can further break down the cost function into this equation right here. The current value of the cost function is equal to the previous value of the cost function plus the current value, D. Okay? So D represents the incremental or additional cost by traversing between the transition paths at Mn minus 1 to your new value S of t, to your new state rather. Okay? So it's actually uh, kind of similar to decoding the D flip-flops where your cost would just accumulate over time. So in this case, for CPM, we have that property also with the cost function that as you go along between time indices or symbol periods, or as you go along your trellis, your phase trellis, the cost function will just accumulate. Okay? So your previous value of the cost function plus the transition, okay, the effect of the transition will become your total cost function. So using this cost function for your Viterbi algorithm, you select the path with the larger cost instead of minimizing it. So it's not the distance per se, it's basically the cost function. You want a larger cost, you optimize your path using the largest value of the cost. Okay? If we let R of t and S of t be these functions right here, where R of t is some phase modulated signal, theta of t, and some correlative phase state rather, theta n, and S of t would be something completely different, the cost function will become this value right here. Recall that this integral represents a low-pass filtering. The addition terms of this multiplied cosine functions, the term with 2 omega ct, becomes approximately 0, which will leave this expression right here. And what this says is that your cost function is mainly dependent only on the correlative state and the phase state. So if you get the difference between them, you're actually getting your cost function D. So the best illustration for that is an example. Let the receive state be, or the receive sequence rather would be, their phases are 0, 0.5 pi, 0, 1.5 pi, and pi, and the initial state is 1.5 pi. Solve for the most likely input sequence. So you start here, okay, and you let the you let the trellis proceed. So from here, you can only transition into 2 at the state pi and the state 0. Okay? So in these cases, we're only going to consider uh, basically this integral right here. Okay? Since we don't have any correlative state, since this is again just one rec, we're only getting the distance between the phase states, which simplifies this problem. Okay? Instead of just integrating, you just need to get the difference between the phases. Okay? And if you look at this transition right here, when you're going to transition from 1.5 pi to pi, you're reducing 1/2 in your state function right here. Okay? So you're reducing 1/2. That means your cost is negative 0.5. Okay? So that's pi minus 1.5 pi. That's cosine negative pi over 2. You integrate that over one period, you get negative 0.5. And opposite is true when you transition from 1.5 pi to 0. Okay? So you actually increase your cost function, it becomes positive 0.5. So at this point, your paths will converge. Okay? And that means you need to look at, again, so you need to look at the path with the maximum cost function. So when you transition from pi to 0.5 pi, okay, when you transition from pi to 0.5 pi, you actually reduce your your output to 0.5 pi, okay, and the distance of that with the receive sequence is 0. Oh, sorry, the cost rather is plus 0.5. Okay, the cost of that is plus 0.5 when you use the definition of cost function, and you add that to negative 0.5, you get 0. Same is true when you transition from 0 to 0.5 pi, you get this. Okay, so 0.5 pi, you add 1, half rather, add 0.5, that's plus 1, you eliminate the minimum. Okay, same is true with this. From these two paths, you transition to 1.5 pi, calculate the corresponding costs, and eliminate the one that is minimum. Okay, and you do this again. So it's the same process. It's a Viterbi algorithm. Okay, same process for Viterbi algorithm, and you arrive actually at a certain path. Okay, so this is the survivor paths for your, or the surviving paths for the receive symbols, or the receive phases rather. And the input sequence is plus 1, plus 1, minus 1, minus 1, minus 1. So that came from the given phase trellis. Right, so that is the Viterbi algorithm, using Viterbi algorithm to decode your uh, CPM signal. Right? A special case of CPM signal, you can use it actually to for a non-coherent detection scheme. This only applies to when your memory, or L, is equal to 1, and only the phase state is considered for the state of the system. Quite easily then, you can get the symbol just by getting the phases of your next state and your current state, take the difference, and that is equal to basically pi h multiplied by what this is your accumulation of the n previous inputs. This is the accumulation of the previous n minus 1 inputs. If you take the difference of that, you'll just get the current input a sub n. And the current input a sub n is basically the phase difference between the next phase minus the current phase divided by pi h. And this will only apply to your on the case that L is equal to 1. This actually simplifies your the modulation process to basically just getting the terminal phase and getting the difference between phases. Right? And it's also robust to noise since you're only getting the phase difference. It also has an inherent timing synchronization since you're only going to get the transition between phases to get the final symbol, A sub n. Differential phase detection can also be used. It's also a form of non-coherent detection. So consider then your R of t, which is the corrupted transmitted signal. You get this. At the time, if you get the phase difference at time t is equal to nt and the next symbol period, you get this phase difference. And by using your differential phase detection, again, just the difference in phase, you select M that minimizes this expression right here. So in this case, it's now a noisy signal. You're bound to have some difference between your received phase and your transmitted phase. So you're going to minimize the phase difference, okay? So based on this definition, you're going to minimize this expression and you choose the symbol M that minimizes that. Discriminator is wherein you use the derivative of the phase. Okay? And by using a discriminator, you can get the transmitted symbol by minimizing this expression inside. Okay? So if you get the derivative of phi s of t, you get the instantaneous frequency of your CPM signal. And that is equal to basically Fc, your center frequency, plus your symbol times the maximum frequency deviation. So if your signal is corrupted by noise, the same as this one, you just get the minimum of this expression inside the absolute value, and you choose the M that minimizes this. But again, it's only applicable to when L is equal to 1. And this is an advantage of CPM over your memoryless digital modulation actually. That timing synchronization is already inherent and you just need to track the phase of your CPM signal. Right? And in this case, it's not a CPM signal, it's just a CPFSK signal. So that's the end of this part of the lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. I'll see you next meeting.